Okay, thanks everyone for being here today. Today we are very happy to have Mark Rudelson from University of Michigan. We will talk about approximately Hadamard matrices and the ray spaces in random frames. Mark, feel free to start at any time.
Thank you. And first, let me say that I'm grateful for inviting me here. This is a joint work with Xiaoyu Dong, who is a graduate student at University of Michigan. And the original problem comes from the signal processing, but we will have several transformations of this problem. We'll quickly see that this problem is rephrased in the language of random matrices. And then from a purely probabilistic problem, we will come to a purely deterministic one, which is of algebraic nature. And this problem in turn will be solved part probabilistically. So let me start with this program. The thing we are going to talk about is frames. And a frame is a method of transmitting a signal in signal processing in particular. Well, it's basically what happens in our cell phones. We want to transmit a signal along a lossy channel. So what we do, we encode it first, and encoding of an analog signal is a system of measurements. The measurements are the inner products of a signal represented as a vector by some other vectors, this system phi, and we get a string of real numbers. Then we transmit this string along a channel. And since the channel is not ideal, the transmission is noisy, but in addition to it, we assume that a few entries of this string can be entirely lost. And we want to see a system which will, of measurements, phi, which will be robust with respect to this process. And this leads to the concept of frame. So a frame is basically an overcomplete basis. So let's call a system of vectors Phi a frame if we can approximately represent the Euclidean norm of any vector using the inner products of this vector against our system. And if we can do it with the norm of the vector, we can do it with the distance between two vectors. So this leads to an approximation. And here in this inequality, there is a parameter k and m, which is a normalizing constant. This is not that important. And the parameter which defines the quality of approximation is r. This is the frame constant. This is the gap between the lower and the upper estimate of the Euclidean norm. And of course, the frame is good if this r is close to 1. Say, if it is of the order of 1, in all this game, we assume that the dimension m and the number of framed vectors m are large, and r is some bounded constant. So one way to construct a frame is very easy. We just take the same basis, repeat it many times, and concatenate them. This, in a way, we get an ideal frame with the frame coefficient 1. And this is a robust way because if we transmit it along the channel, we lose several coordinates. We compare the copies of the coordinates, and when we find many of the same copies, we declare it the real coordinates of the vector. So we are protected this way against the loss. But this is not efficient. There are much more efficient ways to do things. And first, before I go to this, let me say that the basis with respect to which we decompose should not be necessarily orthonormal. We can allow a good reconstruction if the basis is more or less orthonormal, and this will lead us to a concept of a Riesz basis. So what is the Riesz basis? It is a basis which is a good frame at the same time. In other words, it's a basis with a frame constant which is not large. And this way we can, the same way, concatenate Riesz basis instead of the orthonormal basis. But more efficient way is the random frame. So how do we create a random frame? Let's consider an isotropic random vector. This is a vector in Rn, which is centered. The expectation is 0, and the coordinates are uncorrelated, so the correlation matrix is identity. Now I take several independent copies of this vector, and then the law of large numbers means that the average of these independent copies converges to the identity matrix almost surely. And if this is this convergence occurs in the sense of the operators, then I can multiply it from the left and the right by any vector, and I get the approximation of the squared norm. And moreover, since we have it in the sense of operators, we have it uniformly over the vectors in the sphere. Very well, but we don't need the limit. So instead of the limit, we take M large and say that if M is very large, then this equality, which is exact in the limit, becomes an approximate equality for large M, and this will hold for all vectors simultaneously because of the uniform convergence. The optimal M for this was determined in about 1997. And I'm not going to talk about it here. Instead, we are going to consider a different question, the question which was posed by frame theory people, in particular by March and Bonig. And the question is, if we have a very long random frame for which M, would we have this trivial subframe? Would we have a repeated basis or almost repeated basis in it? So first, this is the ideal situation. The frame, the random frame is robust, and this follows from the fact that xj's are random and independent. So if we drop a few of them, we'll still have independent random vectors, we'll still have a frame. So let's translate this to the probabilistic way. Instead of frames, let's consider it in the language of random matrices. Let's consider a matrix whose columns are frame vectors. So we have a fat matrix, M capital is typical much greater than N. And this matrix forms a frame. What does it mean? Since we are talking about the frame property, we can reformulate it in terms of the singular values of this new matrix. And the singular values of the matrix are the eigenvalues of the matrix A transposed square rooted in particular, we need a condition number, which is the ratio of the extreme singular values. So it's the ratio of the maximal norm of the image and the minimal norm of the image. Precisely these constants C capital and C small that we have. So we say that the system X1, Xm is a good frame if the matrix formed out of this has a nice condition number. Okay, and then we can rephrase our problem in the language of random matrices. We have matrices whose columns are IID random vectors, and it is a good frame if the condition number is about 1. And we ask ourselves when this frame contains a trivial subframe, namely the repeated one RIS basis, or even better, a repeated or almost repeated RIS basis. In the language of random matrices, this means that for which M, this very fat matrix contains a submatrix of condition number about 1. The square submatrix this time, n by n. Okay. And here is the answer. We have actually a phase transition. If the number of rows is sub-exponential in the dimension, then there is no RIS basis with high probability. And as soon as we pass this exponential threshold, then the frame contains actually many RIS bases, nice RIS bases with high probability. And many means exponentially many. Of course, in this case, the constant C small is much smaller than this C tilde. By the way, it's a usual agreement in this kind of results that all constants are going to be denoted by C, and I don't care about the values of the constants as long as they are independent of the dimension. So let me formulate this more precisely. First, the existence statement. Let A be a matrix with ID symmetric and non-degenerate entries. Notice that here I don't assume anything about the distribution of the entries, so sorry, besides the symmetry. The entries may not have even the first moment. And let's assume that the number of columns is exponential in the number of rows. Then there is L, which is also exponential in N, such that there exist disjoint subsets of the set 1, etc. M. So there are disjoint blocks of size n, such that if I create a matrix A, a square matrix with n rows and n columns from each block, then the condition number of this square matrix is going to be bounded for all blocks. And this happens with very high probability. Here, very high means not the usual exponentially close to 1, but the double exponential. And all the constants here are depending only on the distribution of entries, which I assume to be IID, and are independent of the involved parameters, and in particular of the dimension. And moreover, the constant alpha is not something crazy. If you trace the proof, you will see that for large dimensions, you can get alpha equal to 4, for example. So these Riesz bases are actually relatively nice Riesz bases. So this is the existence statement. If we have exponentially many columns, then there are exponentially many blocks at the same time for which the condition number is bounded. Let me pass to the non-existence statement. And for non-existence, I need more assumptions. I'll assume that the entries of the matrix are sub-Gaussian random variables. Sub-Gaussian means that the tail of the random variable decays like the tail of, of a Gaussian, at least as fast as the tail of a Gaussian random variable. And this is a natural class. There are many examples of sub-Gaussian random variables. In particular, any bounded random variable is sub-Gaussian. You can guarantee trivially, since we have this coefficient 2 in front, this coefficient, the aim of this coefficient is make this bound vacuous if t is small. So I'll choose a constant k such that for any t in the support of this bounded random variable, this inequality is vacuous, and beyond the support, this probability, this tail probability is just 0. So any bounded random variable is sub-Gaussian. And now let's assume that we have a centered sub-Gaussian random variable, and the number of columns of the matrix is going to be less than some exponential function of n, with the parameter t, and here I have t to the 4th in the denominator. And then let's take a matrix A whose entries are independent copies of this random variable x. Then the probability that there exists a square submatrix with condition number less than this parameter t is very small. And again, very small is even more than exponential in n. It's exponential in n squared. And the constants here depend only on the distribution of the random variable x, and actually on one characteristic of this random variable, on the parameter k, the decay parameter. Okay, so let me pause here for a second and ask if there are any questions. Okay, so there are two statements, existence and non-existence. And the non-existence statement is actually, it requires a proof, but the technique of this proof was developed in non-asymptotic random matrix theory. So since we have only an hour, I'll discuss only the existence theorem, because the existence theorem requires some new argument. So let me start with the existence. And the strategy of the proving of the existence is very natural. we will take a certain nice deterministic matrix, a pattern matrix, which has a bounded condition number. And then we will look at a random matrix, which is close to this one. So more precisely, I sample the columns of my matrix until I find a column which is close to the first column of the pattern matrix. Then I take this column and continue sampling until I find a column which is close to the second column of the pattern matrix, etc. And this way, I form a square matrix when I exhausted all the columns. And then I repeat and get a second square submatrix which is very close to this pattern matrix. And we hope that if we do it, then the perturbation theory will allow us to say that the condition number of the matrix we constructed this way will be close to the condition number of V. If I can get very close to the columns of V, this is indeed true. Yet, it turns out that to apply the perturbation theory, we need to be very, very close to the columns of V, and this will require a super exponential number of samples. So how to fix it? There is an easy modification of this method. And namely, I'll consider the columns which are not very close, but somewhat close to the columns of a pattern matrix. And then I will condition on the fact that my columns are relatively close to the columns of V. And so I get a conditional distribution, but the columns are still independent. And it turns out that this conditional distribution possesses a property that the condition number of this matrix is going to be small with very high probability. Now it is not a deterministic statement, it became a probabilistic statement, but this is good enough because then we can modify our algorithm, and we run the same algorithm, only this time we consider the columns which are not very close to the columns of V, but somewhat close. And we get many copies, many different matrices AJ, and we discard a few matrices which have large condition number. This conditional statement will tell us that what we discard is very few copies. So most of the copies will have a small condition number, and this is good enough for us. This basically would finish the proof of the existence theorem. Of course, model is one thing. We need to look at the columns which are very close to the columns of the pattern matrix. What is this pattern matrix? We need a matrix with a bounded condition number, with a good condition number. The best matrix we can think of is the identity matrix. Its condition number is 1. But this, of course, wouldn't work because our columns are random and the entries are ID. So we with substantial probability, each entry is of the size about 1. We have n of them, and the norm of the column vector should be of order square root of n, and not 1 as for the identity matrix. Well, this example is very easy to modify. Let's take the same identity matrix and scale it by square root of n. But this doesn't work either, because the matrix, the random matrix may have bounded entries, and this is actually important. One of the basic examples are the random plus minus 1 entries. And in this case, we cannot find an entry close to square root of n. And if one thinks for a minute about the options we have for a pattern matrix, one discovers that this random plus minus 1 case is the worst one. The entry of the matrix can be, the distribution can be as small as 2 points. And then if you want to find a random vector which is close to the column of the pattern matrix, then this pattern matrix must have values very close to 2 points, a and negative a, or just a and negative a. Of course, rescaling would make a and negative a 1 and negative 1. So what do we need? We need a matrix with plus minus 1 entries, which satisfies 2 requirements. So the norm of each column is about square root of n. This is automatically satisfied because the entries are plus minus 1. And the second requirement, which makes the thing this difficult, is that the condition number of this matrix should be bounded, ideally bounded by some nice small number. And there are such matrices, Hadamard matrices. So what is an Hadamard matrix? Plus minus 1 matrix is called Hadamard if it is a scaled isometry, which means that it doesn't distort the Euclidean metric, or its condition number is 1. The first such example, which is called a Walsh matrix, was actually constructed not by Walsh but by Sylvester. This is the usual thing in mathematics. Nothing is named after the person who discovered it. And this is the following thing. Let's consider a matrix W2, which is this 2 by 2 matrix. And then there are matrices of size 2 to the k by 2 to the k, which are tensor products of this matrix with itself. Or I can describe the Walsh matrix differently. Let me consider negative 1, 1 as a group, and then the columns of this matrix are characters of this group, in other words, Walsh functions. And there are many more examples of Hadamard matrices. Pele provided two deep number theoretic constructions of Hadamard matrices, and there are actually books written on Hadamard Hadamard matrices and their existence. And the current world record, it was shown that Hadamard matrices exist in dimensions which grow not exponentially in K, like in the Walsh case by polynomial in K, and the smallest power of polynomial is 2.3 something. But for us, this is not enough. We want such matrix in every dimension. And so the known construction do not allow this. And moreover, this is an exercise for combinatorics 101, actually the parity checking, that Hadamard matrices exist only if the dimension is divisible by 4. So if you want this construction in all dimensions, we have to sacrifice the Hadamard property, and instead we relax it. Instead of exact Hadamard, we will consider approximately Hadamard matrices. This will be matrices with ±1 entries. We already know that we cannot afford only 2 values, which are scaled approximate identity, which means that the condition number is about 1. Not precisely 1, but about 1. Okay, so how to construct such matrices? The first thing we can do, if we are probabilist, is to try it randomly. So let's take a random ±1 matrix, and hopefully it will be more or less Hadamard. By the way, yeah. So what we did here, we completed the proof modulus 1 statement, and now if we know that the approximate Hadamard matrices exist, then we have proved the existence theorem. So we reduced a purely probabilistic problem about square submatrices of rectangular random matrices to a purely deterministic one. Does there exist a ±1 matrix with a bounded condition number? So at this point, we can forget about the original problem and concentrate on this purely algebraic problem. So how to solve it? And it is actually solvable, and there exists such a matrix V with ±1 entries, and the condition number bounded by the ratio of C capital and C small. As I said, these are not crazy numbers. The ratio for large n's will be at most 4. And this is a deterministic statement, but the proof relies on a combination of number theoretic and probabilistic ideas. So let me discuss these ideas. The first attempt would be to do it randomly. Take a random ±1 matrix, and hopefully this will work. This fails. This fails the very extreme way. It was proved with Vershinin that the condition number of such matrix is about n and not about 1 with high probability. In this work, the probability was exponential, but now we showed that this probability is going to be even exponential in n squared. And we have n squared random bits, so the construction should be almost non-random. Okay, so the random matrix fails. What else can we do? We know that we have a sequence of Hadamard matrices, and the sizes go to infinity. So let's take a matrix in a larger dimension, which is Hadamard, And let's remove some k rows and columns to obtain the size which we need. Hopefully, if we cleverly remove these rows and columns, we will preserve the Hadamard property. This fails in even a more extreme way. If k is 1, and so if there is an n by n Hadamard matrix, then all its n minus 1 by n minus 1 minors have condition number about n. And this is a deterministic statement. So the only thing we can do at this point is to start looking for an approximate Hadamard matrix from scratch. And we know that we should do something deterministic or more or less deterministic. So we need a class of matrices for which the singular values are easy to evaluate. We'll look in the books or in Wikipedia and find such class. This is circulant matrices. So circulant matrices are matrices generated by one vector, v1, etc., vn. I put it in the first row. Then the second row is v2, v3, etc., vn, v1. And then the third row, v3, v2, etc. And we continue this way. And the circulant matrix is normal, which means that its singular values are absolute values of the eigenvalues. And the eigenvalues are easy to evaluate. They are the Fourier coefficients of this of the generating vector, this vector v1, v1, etc., vn. So we have to find a generating vector, a vector with plus minus 1 coordinates, whose discrete Fourier transform has absolute value close to a constant. And again, we search the books and find almost what we need. At least if this n is a prime number. So suppose that q is an odd prime, then there exists a vector whose coordinates are plus minus 1, and the Fourier transform has absolute values close to square root to the same number with very small error. The error is much smaller than the square root of q. And the proof is a combination of deterministic and probabilistic ideas. So the first one is what I hinted before on. It's an existing construction from elementary number theory. This is the Legendre symbol, or quadratic character. Instead of vectors indexed by 1, etc., q, I consider vectors indexed by the field z mod q. And in this case, we can define the set of quadratic residues. These are the set of numbers in z mod q, which are squares mod q. And then the Legendre symbol is 1 for quadratic residues, -1 for non-residues, and 0 at 0. This is a very well-known function in number theory. It was studied from the 18th, basically from the late 18th century. And its Fourier transform is defined by a Gauss sum. And it has a constant absolute value square root of q everywhere except at 0. So what we get is a vector which almost serves our our purposes. It is it is plus minus one vector, except for that it's zero, and its Fourier transform is constant, except for 0. If we change these values, then to v of 0 to 1 or minus 1, and we had to something close to square root of q, we are done, at least for prime n. And changing v of 0 is easy. I just replace v of 0 by, say, -1. It's not a big deal. The impact on the Fourier coefficients will be negligible. Changing the Fourier coefficient is more difficult. And here is the point where the probability comes in. So let's take the new sequence of coefficients, this UQ. We keep -1 as Legendre symbol for non-residues, for quadratic non-residues. And for the quadratic residues, we introduce independent random variables, replacing the original value 1 by -1 with some probability. Which probability? The probability is chosen so that in average, the 0 Fourier coefficient will be what we need, square root of q. And then, again, the Gauss sum calculation shows that the difference of the average value of the other Fourier coefficient and square root of q, which we want, is about 1. Actually, it will be either plus or minus 1. So in average, we are in a good shape. Then, if we are in a good shape in average, we try to do what we usually do in probability. We try to rely on measure concentration to say that what happens in average happens with high probability as well. And this is indeed true. And this allows to construct approximately Hadamard matrices for all prime sizes. Well, now we have to extend it to all possible sizes. And any number is a product of primes. And Hadamard matrices have a nice property that if we have Hadamard matrices, then their tensor products are also Hadamard. So let's take these approximate Hadamards and let's tensorize them. Hopefully it will be approximate Hadamard. They will be not. Despite the fact that these matrices are very close to Hadamard, there are errors, and these errors decay quickly to 0 when the prime factors go to infinity. But imagine that n contains a prime factor, say 3 to 1000. Then we accumulate the same constant error, and the error will be as large as one wish or one doesn't wish. So we cannot use this construction with infinitely many terms. Well, so this means that we want to use these blocks, which we already constructed, and we want to use a bounded number of blocks. Is there a way to construct a natural number from a bounded number of primes? Actually, this is one of the pinnacles of the analytic number theory, and this is Vinogradov's sum of 3 primes theorem. Let me consider a modification of it for even numbers when we have not 3 but 4 primes. So let's assume that we have a sufficiently large even natural number. Then this number can be represented as a sum of 4 primes, and moreover, these primes can be as close to n/4 as we want. Okay, now we have 4 primes. For each prime, we have an approximate Hadamard matrix, and our size is exactly the sum of these 4. We want to construct an approximate Hadamard matrix from these 4 blocks. The easiest way would be to stack them diagonally, because the sum of the sizes is exactly the size we want. But this wouldn't work. The block diagonal matrix will be an almost isometry. But we have a large empty blocks, and we ran out of material. We already used all 4 matrices. So instead of stacking them diagonally, we want to stack them next to each other, but the sizes are different. So what can we do? We work like tailors. If the sizes are different, we cut them to size. Instead of the bigger matrices, we cut and put aside a few bottom rows to make all the number of rows the same. And then we consider just all top matrices. And this can be easily put next to each other. And the resulting matrix will be approximately a scaled identity. A scaled isometry, but it is not going to be a square matrix, of course. It's a rectangular matrix. So how to make a square matrix out of it? We can try to repeat this. Repeating will make each this block row a scaled isometry. But this is not a matrix with a nice condition number. Actually, it's degenerate. This matrix has many rows which are the same. How to deal with it? Let's take a 4x4 Walsh matrix and multiply these blocks by the entries of the Walsh entry-wise. And then it turns out that this matrix, this new product, will be a scaled, more or less a scale isometry. And this approximately equal is very precise. Actually, if you think about what happened, this is a poor man's substitute to the tensor product. I tensorally multiplied this by the first row, but since the entries are different, it's not really a tensor product. Well, this is much better. The matrix is almost square, but not yet squared. Right? The number of rows, the number of columns is n, the number of rows is 4 times the size of the smallest block. So we have to complete it and create a bottom part of this matrix. This was the top part. We started working like tailors, so let's do it like tailors. We had ends and odds. We had these bottom parts which we cut out. And let's create the bottom part of the matrix W by putting these bottom parts diagonally, like we originally thought to do. In this case, this matrix V bottom will have a right number of columns. So if we consider W top, W bottom, it will be a squared n by n matrix. But it retains the same problem. We have empty blocks and we ran out of material. We already used the top part and we already used the bottom part, and we cannot stack them next to each other because these bottom parts are of different sizes. And moreover, for the last block column, for U4, we don't have anything. This is an empty column. So what do you do if you ran out of the material? Well, if you don't know what to do, you try to do something randomly. You just take IID random blocks. And it turns out that this works. This works with high probability. So to summarize, at least in the even case, how do we construct the matrix? This is a 7x4 block matrix, which has 9 completely random blocks and yeah, 9 completely random blocks and 19 blocks which are black, which are probabilistically perturbed blocks created using number theory. So the purely random part, the red part, is indeed small. There's the number of columns is epsilon n, and the number of rows is epsilon n, the number of columns is n, so it's epsilon n squared, and this matches what we said. We cannot allow more than epsilon n squared purely random bits. But with these random bits, we managed to construct an approximately Hadamard matrix. And with this construction of the pattern matrix, we can complete the proof, at least in the case when n is even. The case of odd ends is marginally more complicated, but since my time is up, let me stop here.
Okay, thank you very much for a very beautiful talk. Any questions or comments? Maybe I can ask a question. So all these results are very beautiful, and they mainly deal with the real number case, right? Real matrix case. How about the complex case? I see some notion like complex Hadamard matrices. I don't know if they can be interesting in this problem.
First of all, if we solve it in the real case, any real matrix is automatically complex, so the problem is
yes.
solved here. Second, I believe that the complex problem should be much easier because instead of my matrices whose entries take only values plus or minus ones, we can take all values of absolute value 1, and there are much bigger freedom in it, in particular in using Fourier analysis. You don't deal with the finite groups anymore. So the construction, I anticipate that there will be a much easier construction in the complex case. But on the other hand, we don't need it because we already did it in real one case.
Yes, okay. Thank you very much. Any other questions or comments? Maybe the last question from me. Could you please comment a little bit about the odd case? What would be the similarity and what would be the difference?
Yes. The difference is we try to repeat the same thing. But, and there is some theorem, Vinogradov's 3' theorem for odd case. Actually, this is why it is called 3 primes. Any odd number is a sum of 3 primes. But if we try to repeat it, we encounter one obstacle. The obstacle is that there is no 3 by 3 Hadamard matrix. The size should be divisible by 4. So instead of this, we do it a little differently. We look in these books about exact Hadamard matrices and find a construction of Hadamard matrices of a certain size. The size is basically n cubed, L cubed, 2 logarithm base 2, 2 to the power 2 logarithm base 2 is L squared times L. It's basically L cubed. And L cubed is a nice sequence, which means that L cubed plus 1 over L cubed tends to 1. And this means that we can find an element of this sequence in the interval 1 minus epsilon over 4n, 1 plus epsilon over 4n. And then we use this Hadamard matrix, exact Hadamard matrix, for this number. And we subtract this number m of L from n. M of L is even, n is odd, so the difference is odd. And the odd number is decomposable into 3 primes. So we have 3 matrices plus another one which we got from this construction. We have 4 matrices altogether, but then the previous construction applies.
Okay, very nice idea. More questions or comments? Okay, if not, then maybe let's stop today here. Thank you very much for a very nice talk.
Thank you.
Okay, have a nice day.
You too. Thank you.
Bye.